Okay, so I hope you are able to understand what we are trying to say. So now suppose we already know that PV is equal to nRT. If it was an isothermal process, PV was a constant. If it's an adiabatic process, PV power gamma is a constant. If PV power gamma is a constant, dP into V power gamma plus P into V power gamma minus 1 into dV is equal to 0. In other words, dP into V power gamma is equal to minus P into V power gamma into dV by V. This V power gamma here gets cancelled. So I have dV by V is equal to minus dP by P. Then I know that the bulk modulus B is equal to P divided by delta V by V. But for a gas, understand that it is not equal to P divided by delta V by V, because a gas will always have a pressure. If you want to change the volume of a gas, you have to only bring about a change in pressure. So for a gas, B is equal to dP by delta V by V, and it is going to be a compression, so the negative sign. So from there I can say that P is equal to minus dP by del V by V, but this is nothing but the bulk modulus. So for a gas, P is equal to B. In our case, when you have differentiated this, you will get a gamma here. So when you get a gamma here, what will happen is everything else will remain a constant, remain the same. You will get gamma P. So this gamma will get associated with P, and you will have a gamma P. So you will have that the bulk modulus is equal to gamma P. If you assume it to be an isothermal process, the bulk modulus is equal to P. If you assume it to be an adiabatic process, the bulk modulus is equal to gamma P. So we said that velocity of a gas is root over of gamma, velocity of sound in a gas is root over of gamma P by, or gamma RT by M. I am not going through that part of the derivation again. Or simply speaking, it is equal to root over of gamma P by rho, where rho is the density, mass by volume, P is the pressure, gamma is the adiabatic constant. Okay, so now if you have understood this, the next thing that we have to understand, so what we understand so far is that there is a displacement wave, S is equal to S0 sine omega t minus kx. There is a pressure wave, P is equal to P0 cos omega t minus kx. And there is a density wave. Then I have also explained to you that P0 is equal to BKS0, where B is the bulk modulus, K is the 2 pi by lambda, that is the wave number, and S0 is the displacement wave. Okay, so this part is already understood. Now a wave is a traveling disturbance. It can also be said to be a mode of energy transfer. It can also be said that it's a mode of energy transfer. So now the question is, how much energy is transmitted in a wave? How much energy is transmitted in a wave? So now if you go by our earlier arguments, see, if you have a small portion of the gas here, this portion of the gas is applying a force on the other portion, and that force is equal to P into A. Now this is going through a displacement of delta S, right? And this is the work done. This work done per unit time is the power or the intensity. Okay, so the intensity of the wave is equal to this much. So if the intensity of the wave is equal to this much, let me substitute. My P is equal to P0 cos omega t minus kx. My ds by dt, ds by dt is equal to S0 omega, again a cos omega t minus kx, so I put a square here. Okay, so the total work done will become, or the intensity of the wave I is equal to P0 S0 omega, P0 S0 omega into cos squared omega t minus kx. Okay, now already we have said is p0 is equal to bks0. Yeah, so if I substitute that bks0 here, I'll get bks0, and this k is equal to omega by k is equal to v. So k is equal to omega by v. So when I substitute that, I'll get b omega squared s0 squared cos squared omega t minus kx by v. Okay, so from here I'll rewrite the expression again, that the intensity of the wave is equal to a omega squared s squared b by v into cos squared omega t minus kx. That means as time varies, the intensity, the power intensity also is varying as a cos squared function. So it is varying as a cos squared function. So the power is not a constant. But in one time period we can find out what is the average power. So the average value of cos squared is half. So that is, you have learned that in AC currents. So when I apply that half, so I'll get half into A into omega squared S squared B by V. Now this omega squared is nothing but 4 pi squared frequency squared. Omega is 2 pi f. So omega squared will become 4 pi squared f squared. So this becomes, the intensity becomes area into s squared into b into 2 pi squared f squared by v. Okay, so the moral of the story is, remember, okay, here also there can be more shortcut. I can simplify it further. So let me just write it. So a into, I'll have b squared s squared, this frequency squared is I'm having omega squared here. Instead of omega squared I can say v squared into k squared. So I'll say it is k squared, there's a v squared and v in the denominator, v, okay, by 2 b, because I squared b, I'll put a b here. So now that bks is nothing but p naught. So I can say it is equal to p0 squared into a into v by 2b. This is the energy transmitted. Now we are interested in the energy transmitted per unit area. The intensity is nothing but energy transmitted, power transmitted per area, per unit area. Okay, so when we have that per unit area, when it is coming in, that is per cross sectional area, that area term will vanish, and I'll have my intensity is equal to P0 squared V by 2B. Alternatively, remember that the intensity is proportional to square of frequency. The intensity is proportional to square of amplitude. So remember this, that the intensity of any wave is always proportional to square of frequency into square of amplitude. This is how for a sound wave you work. Okay, you have to be familiar with this kind of working. This will help you for the JEE Advanced. Okay.